Today we're going to be continuing our discussion with derivatives. We're going to be looking at another derivative rule, which we call the chain rule. So we'll be dealing with that later on. But we're going to start by looking at this function here and taking this idea, this problem that we've done in the past where we've written a tangent line equation at a specific location. We're going to tweak it just slightly. So in this question here, we're going to find the tangent line equation. We're still going to write that. But instead of giving an x value, instead of giving us a location, we're told that we want it so that it's wherever my tangent line has a slope of 1. So we want the point where m is equal to -1. So instead of knowing our point and trying to find our slope and then writing our line equation, this time I know what my slope is and I want to write my line equation. I want to write the point for that line. Or I want to find the point so I can write my line equation. So I want my slope to be -1, and thinking through tangent line slopes and how they're connected to our function, we would know that then we want our derivative at some x value to equal -1. And what we need to do is we need to work backwards to say, okay, well, what x value would make my derivative -1? So my tangent line slope is -1. And then once I know the x value, we can find our y value. Okay, so let's start by finding our derivative. So I have my function here. My function is f of x is equal to 1 over the square root of x minus 3. And we have a lot of different rules now that we can use. We can use our power rule, product rule, quotient rule. And I want to pick the one that is most appropriate for this problem. And immediately you might say quotient rule. It's a fraction. And you wouldn't be wrong. Like you could do your quotient rule on this, but remember how long that quotient rule is? Low d high minus high d low all over the square of what's below. And while that is a useful rule, and a lot of times we are stuck, we have to use it, and it's good to have. If we can rewrite, if we can algebraically manipulate our function to make it something simpler, so we could use either the product or the power rule, it might be in our best interest to do that. So looking at my function here, I'm going to say, okay, well, it's just a 1 in my numerator. So 1 over, the square root of x minus 3, I can think of this as a negative exponent if I had an exponent, which I don't, have written down, but I have a square root, and square roots are really just fractional exponents. So I can rewrite my function as x minus 3 to the -1/2. And now you can see how this might fit better for the power rule. And the power rule is nice and simple. So we like the power rule. Now this is a little bit different than our typical power rule. Now our power rule was defined. We said our derivative of x to the n. So we're talking about raising x to a power. Here we have x minus 3 being raised to a power. Is that going to change how I handle my derivative? For this moment, we're going to assume, we're going to make an assumption, because we don't know anything otherwise. We are going to assume the power rule will work just fine. Later on, we're going to see if that was right or not, if it was okay to make this assumption. But we are going to assume that the power rule is going to work just fine. So that means f prime of x, my derivative here, is going to equal -1/2 times x minus 3 to the -1/2 minus 1. Or, cleaning that up a little bit, -1/2 times x minus 3 to the -3/2. -1/2 minus 1 is -3/2. And I can rewrite this back into the square root, and my x exponential format if I want to, which since I'm going to end up setting this equal to -1 and solving, I actually am going to do that. It's going to make my life just slightly easier. This is going to be -1 divided by 2 times the square root of x minus 3 squared. Isn't that so pretty? Such a beautiful derivative. All right, but there's my derivative. There's my f prime of x. And so going back over here, we said, okay, I want to know where on my function does my derivative equal -1? Where is my tangent line slope -1? So we are going to take our function's derivative, this f prime of x, and we're going to set this equal to -1. So I'm going to zoom back in so we can see this a little bit better. So that means -1 divided by 2 times the square root of x minus 3 cubed. I apologize, that should be a cube, not a square up there. It was -3/2 is our exponent. Sorry about that. And then we're going to set this whole thing equal to -1. So I have -1 equals -2 times the square root x minus 3 cubed, or positive 1/2. Just playing with some algebra here. So then 1/4 is equal to x minus 3 cubed. So I have 1 over the cube root of 4 equals x minus 3. So x equals 3 plus 1 over the cube root of 4, which if I'm going to rationalize that, my goodness, is 3 plus the cube root of 16 over 4, which, you know what, we're going to approximate that. We're going to do that. We're going to do 3 plus the 1 over the cube root of 4, and we get x is approximately 3.629960525, and that just keeps going. There's my x value. Beautiful. And you can see on your graph, if I were to go where x is 3.62999, or close to there, we have this point here. And you could see, if I were to do a tiny little tangent line, that looks like it has a slope of about -1. So that's not, you know, a rigorous way to check our work, but it's a good little visual. Okay, that looks correct. It looks like it makes sense to us. There's my x value. Now I just need to find my y value. I need to figure out what my f of 3.629960525 is, and this is f, not f prime. So I'm going to go back to my original function. I'm going to substitute this in, and I'm going to have that y, my output value here, is 1.2599210.5. So altogether, my tangent line slope is -1. My point is 3.629960525, comma 1.259921505. So y minus 1.2599210.5 equals -1 times x minus 3.629960525. And we could round these. That's fine. Just, you know, be exact. I'm just going to be exact. But we could round these. Typically in calc, you'll round to 3 decimal places, the nearest thousand. But we would get -x plus this 3.629960525 plus 1.2599210.5. And so adding that together, we have my line is y equals -x plus 4.889 8.81575 in my slope-intercept form. And again, whoops, we want to make that no fill. There we go. You can see if I were to continue this line that I started drawing, or if I look, I'm going to pass my y-intercept right about there. You can see I have my tangent line equation. All right, this thing right here, where we made an assumption, we made a pretty big assumption that the power rule was going to work just fine, even if it wasn't x being raised to the power. We're going to come back to that later and see if that was valid or not. See if everything we did after that was just nonsense or if it was actually okay.
See how our calculator is going to be really helpful in helping us figure out a derivative at a specific point. Now, our calculator, as powerful and as capable as it is, cannot give us the algebraic derivative function. But it can, by using approximations, give us the value of our derivative at a specific point. And it can do it two different ways. So depending on what your problem is asking you to do, one way may be better than the other. The first way we're going to look is by using the graph, using the graphing feature of our calculator. So if I go into y equals, we are going to look at this function here, e to the x times sine of x, and we're going to calculate the derivative at the point where x is equal to 1. Actually, no. We're going to do it where x is equal to pi. Yeah, we're going to do this where x equals pi. And we're going to do this, and we could do this by hand. We could take our product rule, do 1d2 plus 2d1, and we could figure out what our derivative is, and then we could evaluate the derivative at pi, and we could get an answer back. But our calculator can do this for us, so this is really helpful if you are looking to do a tangent line equation. If you want to do the tangent line equation, you need to know a slope at a particular point. You need to be able to find the coordinates of your point as well, and the graph can help us here. So we're going to graph our original function, not the derivative. We'll graph the original function, and you want to make sure that you are in radians here. Since we're going to be evaluating this at pi, we want to be in radians. And so if I graph this, and I'm going to do zoom 6, so we get that standard graph, we'll see it starts off, kind of looks like exponential, dips a little bit, and then we have this funky little thing going on. And it's growing really large like the exponential does, but the sign is creating that wave. So unlike exponentials, this will become negative. And we could zoom out, we could see a little bit bigger of the picture, but it's just going to have that same motion over and over again. Okay. This is my function. Let's say I'm at pi. So pi is at, 3.14. So we're going to be down here somewhere. Okay. And I always say, okay, I want the tangent line equation when x is equal to pi. I can hit second and then calc. So that trace button right above it, you'll see it says calc. And I'll open up this menu, this calculate menu, and this is where we can do values, we can do zeros, minimums, maximums, intersections, and then you'll see 6 and 7. 6 has our Leibniz notation, dy dx. 7 is something called an integral, which you will learn about next year in calc. But in 6, dy dx, if I choose calc 6, it says, okay, calculate the derivative at a point. Your calculator will tell you what you're doing. It says calculate derivative at a point. And it says, do you want it at the point x equals 0, 0? And you could hit enter and it'll give you the derivative at that point, or you could scroll through, you could arrow over. The most efficient way to do this though, is if I type in a number, like the number pi, it'll say x equals pi, hit enter, and it will give me 2 pieces of information. First, it gives me my x value, x equals pi, that 3.14. It gives me my y value, 0, which should make sense because sine of pi is 0. I said it was down below earlier. I was thinking cosine in my head. But sine of pi is 0. And then right above it, it says dy dx. There's my derivative is going to equal, and the notation is a little off because it should say the derivative at this point, but that's a little too much for the calculator to fit in there. But it says it's equal to negative 23.1407. And you can see how steep that line is decreasing. It is decreasing very quickly. So it should make sense that that slope is pretty large in the negative. But now I have all of the information I need in order to write my tangent line equation. Now, the slight downfall with this is, okay, we know there's probably an e to the x somewhere in there, so we have an e to the pi. This will only give us decimal approximations. So if you need an exact slope or exact tangent line value, then doing it by hand might be helpful. And then the other thing is your calculator will only do the first derivative. So if you're looking for the second or the third derivative at a particular point, you'd have to take your first derivative by hand and then use this on that first derivative to get the second derivative at a particular value. So there's no second derivative option here because remember your calculator will not do the algebraic derivative. It won't give you the function, but it can, by approximations, give you the slope, the tangent line slope at a particular point or the derivative at the particular point. Okay, so what we did, I'm going to walk you through it one more time, is, all right, we had our function graph. This is our original function, and we want to take the derivative at a particular point. So I hit second trace or second calc. It's my sixth option, the dy dx. I say what point I want it at. So I can do it at any point I want. If I want to hit pi, I'd do pi. If I wanted it at 2, I would hit 2. Either way works. And then it gives me all my information. It gives me my coordinate point, x, y, and it gives me my slope. The other way that you can do this, which is going to be a little bit more helpful for just looking for a derivative, we don't necessarily care about the location, the y value. I don't necessarily need to see the graph of it. In my standard screen here, I can go to my math catalog. This math button is so very helpful, and you're going to use it quite often in calc. But if I hit that math catalog, I have my fraction button, I have my cube root, I have a min, I have a max. Notice in 8, it says n derivative. This is a numerical derivative. This is saying it will take a derivative of a function at a point. This is the same thing as on the graph, the Calc 6 option. This is my Math 8 option. And what I need to do is I need to give it some information. I need to tell it which variable I'm taking with respect with, which is always for our purposes going to be x. So I'll put an x in there. And then inside my parentheses, I'm going to type in my function. So I'm going to put in e to the x, sine of x. And then down here, this vertical bar is notation to mean we are going to take whatever we get as the derivative and we're going to evaluate it. So that vertical bar means evaluate. Plug an x value in. So I need to tell it what x value I want to plug it into. So I'm going to hit second and then pi because I want to evaluate this at pi. And I hit enter. And I see negative 23.1407. And it's the same number, a little bit more detail. We get a little bit more decimal points here. We have that same number that we saw up above. This way is helpful if I need to use this number in some sort of calculation, because now I have access to it. I can hit, second answer. I could arrow up, highlight it, copy, paste. So if I need to use that number in a calculation, doing it outside of the graph is a little bit more helpful. Okay, so there's 2 different ways your calculator will give you the same information. Depending on what you want to use that information on, one might be more helpful than the other. All right, so this one, what we did again, one more time, we hit the math catalog. We went down to math 8, so the numerical derivative. We said we want to do it with respect to x. We always do it with respect to x. That's never going to change for us. We have our function typed in, And then down here, we have to put in where I want to evaluate it. And then I get my answer back.
All right, so I know we're jumping around a little bit, but I want to go back to that idea if you're given the graph of a function, being able to sketch the graph of the derivative. And so, all right, we have our function. We're looking for a sketch. I'm not looking for an exact graph of our function. You can't do that if I don't even have the function, the original function. So if I know what the original function is, then I could take the derivative using some of the rules that we've been talking about, and then I could graph it that way. But if I'm just looking for a sketch, the only things that we need to be absolutely correct on are the zeros of the derivative, and then where is my derivative positive and where is it negative. And we can get that all from our sketch. So we did this a little while ago. If you remember how to do it, go ahead, pause the video, try it on your own, and then come back and we'll check. All right, so the process here is, okay, I have to be exact on two things. Where are my zeros? Where are the zeros of my derivative? So my f prime of x is going to equal 0 where, and whenever I talk about where, it's always an x value, where f of x has a horizontal tangent line. Okay, so I don't care about the y value, I care about the x value, because where the y value is on the function, that doesn't really matter, because when I go to do my derivative, that's going to be an x-intercept. My y value is 0, my f prime is 0. So the where is always an x value. But I'm looking for where does f of x have a horizontal tangent line? That's the same question as where does f of x has a max or a min? Where does f of x have a relative extrema? Those peaks or those values. So looking here, I can say, okay, I'm going to have a horizontal tangent line up at that maximum. That is at the location where x equals 4. So what the y value is, that's not important in this process. It's the x value. My x value is 4. My horizontal tangent line is when x is equal to 4. That means at 4, f prime is going to equal 0. So if I go to graph this, I'm going to have a x-intercept. I'm going to cross the x-axis when x equals 4. Now, whether or not I cross from negative to positive or positive to negative, we don't know that yet. We'll figure it out. That's the second thing that we have to be absolutely correct on, is where is my derivative positive and where is my derivative negative? If you recall, your derivative has to be with the slope of your tangent lines. So if I want to know where f prime of x is positive, that's asking where are the tangent lines, where are the tangent line slopes positive, which is the same thing as asking where is f of x increasing? Okay, so think about it. If f of x is increasing, and I draw some little tangent lines, all of these little tangent lines are going to have positive slopes. So that means if I am to the left of 4, I need to be above the x-axis. I need to be positive. How, sharp my slope is there, how steep that line is, I don't know. Frankly, it doesn't matter. But I do know I need to be positive. I need to be above the x-axis. Where my derivative is negative, similar idea, that's going to ask where the tangent line slopes are negative. Or where f of x, my function, is decreasing. So when f is decreasing, f prime is negative. So that means to the right, if I look here, I'm falling. My function is falling. So to the right of 4, my derivative has to be negative. And again, how steep doesn't really matter. I need to be accurate on, I guess, 3 things. These 3 things right here. Where does f prime equal 0? Where is f prime positive? And where is f prime negative? When we're talking about a sketch, those are the things that we need to be accurate on. Now, if I go and look at my answer, you can see I was a little bit steeper than I really wanted to be. But again, unless I actually know what my function is, which I didn't tell you that, there's no way for you to be 100% accurate. So that's not what we're looking for when we do these problems. We're looking for where is the derivative 0, where is the derivative positive, where is the derivative negative. That's what we care about. All right. We have been learning a lot of derivative rules. We learned the power rule, which most people tend to enjoy. And then we learn the product and the quotient rules. And those are a little bit more involved. They take a little bit more time. They're a little bit harder to wrap our heads around. So we're going to do a quick little review of those. And then I'm going to introduce a new rule, the chain rule. Product rule is when you're asked to take the derivative of a function times another function, when you have a product of your functions. And so it's something like this, d dx of f of x times g of x. So we have a nice little ditty to help us. I'm going to call them function 1 and function 2. In function notation, I'm going to write f of x times g prime of x plus g of x times f prime of x, which is all fine and good, but it's not the easiest way to remember it. The easier way is to say this is 1 d2 plus 2 d1. And there's your product rule. So we're going to do an example. And you can try this one on your own. You can pause the video, give it a shot, see how you do, and then come back. So we're going to do the derivative of e to the x times the square root of x. Now before I get too far, I'm actually going to change it just slightly. That square root of x, I'm going to write that instead as x to the 1/2. It's just going to make my power rule a little bit easier to deal with. But now I can use my product rule. 1d2 plus 2d1. 1 is e to the x times d2 is 1/2 x to the negative 1/2 plus 2, so x to the 1/2 times d1, the derivative of e to the x, it's my favorite, e to the x. And that's it. I could go through and I could rearrange this, and I'm going to put the 1/2 x to the negative 1/2 in front of the e to the x plus x to the 1/2 e to the x. And I could factor out an e to the x if I wanted to. I could put that the fractional exponents, I can put them back into the square roots. I'm not going to. I'm going to leave it this way. Oh dear. Let's try this one more time. All right, that's fine. Here we go. Nope. All right. What do I do now? There we go. All right, we're going to try one more box. Oh, so close on my coloring. We're going to fix that. There we go. All right, so there's my product rule. 1d2 plus 2d1. Quotient rule also has a nice little ditty to help us remember. Top function, our numerator, I'm going to call that high. Bottom function, denominator, I'm going to call that low. And I'll write out what it is in our function notation. It's not so fun, but that's okay. Always start low. So we're going to do g of x times f prime of x minus f of x times g prime of x. I had to sing the song in my head for just a second so I could write this out. All over g of x squared. Now that one, you can memorize that form if you want to. Go ahead, be my guest. Clearly I don't, because I just had to sing the little song in my head to remember how to write this out. This is more easily remembered and more commonly known as low, D high, minus high, D low, all over the square of what's below. Which you normally don't say it that slowly, but we're learning. We're still getting used to this. This is new for us. If I said it a little bit faster, it's a little more fun. Low D high minus high D low all over the square of what's below. You always start low. Just start low and you go up from there. You're good. All right, so we're going to do an example. And again, you can pause the video, try it, and then come back and see what you get. We're going to take the derivative of e to the x over the square root of x. And I really could, if I wanted to, make this into a product by making that over the square root of x, x to the negative 1/2 times the e to the x. I can make it into a product, but we're not going to do that. We're going to do our quotient rule. We're going to do our quotient rule. I am, like I did before, going to change the square root of x into x to the 1/2 because that power rule is just going to be so much nicer. We can do our quotient rule. So quotient rule says we start low. So x to the 1/2 times d high, the derivative of e to the x, just e to the x, minus high, so e to the x, times the derivative of low, so that's going to be 1/2 e to the negative 1/2. Oh, so sorry. I don't know what I was thinking. 1/2 x to the negative 1/2 all over the square of what's below. So this is x to the 1/2 squared. And I could leave it like this, but I'm going to go one step further. I'm just going to do a little bit more rearranging. I'm going to leave it as x to the 1/2 e to the x, but I'm going to pull that 1/2 e to the negative 1/2, 1/2 x to the negative 1/2 in front. So I'm going to get negative 1/2 x to the negative 1/2. Try this again. X to the 1/2 e to the x minus 1/2 x to the negative 1/2 e to the x. So all I did was move this in front. That's it. That's it. And then we're going to put that over. I'm going to simplify. X to the 1/2 squared is just x. And there's my quotient rule. Don't need to plate that out. There we go. There's my quotient rule. Oh, see, now this is going to bother me. That's better. I feel better. Don't you feel better? I feel better. All right, so we have our product rule, we have our quotient rule. They both have these nice little rhymes, these nice little songs to help us remember. What we're going to talk about now is what we call the chain rule. And the chain rule is what we do to find the derivative of a composite function. And unfortunately, I don't know any little song or ditty to help us remember the chain rule. If you know of one, or if you come up with one, share. Let me know. I would love to hear it. I don't currently know one though. What we're going to do is we're going to take a look at that function we started off at the beginning, and we're going to see if our assumption that the power rule works just fine on that problem was it valid or not. Because this function here, this f of x equals 1 over the square root of x minus 3, is a composite function. And derivatives of composite functions have a special rule that they have to follow. I'm going to start by just rewriting this function. Okay, the way we wrote it before was x minus 3 to the negative 1/2. And then we said the power rule. We used our power rule. We made an assumption about the power rule. We're going to see if we were right. So we're going to hang on to that for just a second. But you can see how this is a composite function. We have an inside function of x minus 3. And we have an outside function of something to the power of negative 1/2. So we have an inside function, we have an outside function. The chain rule says if you want to take the derivative, d dx, of something like f of g of x, So my inside function is g of x, my outside function is f. The chain rule says you're going to start by taking the derivative of the outside. So if the outside's a power, you're going to do the power rule. If the outside is sine, you're going to do the derivative of sine. You take the derivative of your outside function, but you leave the inside function alone, at least to start off with. So the inside function stays as it is while you take the derivative of the outside. But then you have to multiply that thing by the derivative of your inside function. That step we did not do at the beginning of class. We didn't know to do it. We didn't know there was even a thing called the chain rule. So we didn't know to do that. We didn't do that. We're going to see if we just completely messed up that entire problem at the beginning of class, or if we managed to luck out. So we are going to rederive, we're going to refind the derivative of x minus 3 to the negative 1/2. We're going to start. So I'm going to start by identifying my inside and my outside functions. So my inside function is x minus 3. And my outside function is something being raised to the negative 1/2. And it's kind of, this one isn't so hard to see that it's a composite function because you have those parentheses. So you're literally putting something inside of the parentheses that's being raised to the power. So you have your inside, you have your outside. We're going to start by taking the derivative of the outside function. So the derivative of the outside function, the derivative with the power rule says, okay, we're going to bring down the negative 1/2. And then we're going to change our exponent to be negative 1/2 minus 1, which is negative 3/2. There's my outside function. There's the derivative of my outside function. And what I'm going to do is I'm going to leave the inside function the same. Okay, so we took the derivative of the outside, we left the inside the same. But now what we need to do is we need to multiply by the derivative of the inside function. So I need to know what is the derivative of just x minus 3. No power to it, just the inside x minus 3. What's that derivative? So that's a power rule in and of itself. So I look at the derivative of x that has a coefficient of 1. That's just 1. Minus the derivative of 3, but that's a constant. So that derivative is 0. So this is just 1. So I'm just multiplying by 1. Oh, my goodness, what a lucky day we have. When you multiply by 1, nothing changes. So we didn't completely mess up the first problem. We got lucky. We did, however, make a really bad assumption. Because it's not always going to be the case where the derivative of the inside function is just 1. So while the one we did worked out, it's not a practice we want to get into of just assuming things are going to work the way we want them to work. And I know I told us that we were going to do it, so this is my fault, but just, trying to learn a lesson there. When you have a composite function, you have to follow the chain rule. Because watch what happens if I just make one slight little change. If instead of doing the derivative of x minus 3 to the negative 1/2, I make it 2x minus 3 to the negative 1/2. All right, my outside function is still the same. My inside function is 2x minus 3. So I'm going to start the same way. I'm going to take the derivative of my outside function. So it's going to bring down the negative 1/2. My new exponent's negative 3/2. And I keep the inside, 2x minus 3, the same. But now I need to multiply by the derivative of my inside. So we need to figure out what is the derivative of 2x minus 3. This time, it's 2. So the derivative of my inside function is a 2 now, not a 1. So now my final derivative is negative 2x minus 3 to the negative 3 halves. This time, the chain rule matters. It's not the same thing as if I just assume the product rule or the power rule works the way I want it to. This time the chain rule affects my derivative. Just one slight little change. Just multiplying that x by 2 makes this a whole different process. So we lucked out at the beginning, but we made a bad decision in making that assumption. We have a chain rule. Now, again, I don't have a nice little ditty to remember the chain rule. If you can come up with one, please share. But we have our chain rule. The derivative of f of g of x is f prime of g of x times g prime of x. We're going to do some examples. Okay, so I'm going to try and get that to squeeze in there. And I'm going to pick a different color. We're going to take the derivative of sine of x squared. And again, this might be one that's a little bit easier to see your inside and your outside functions. Inside is going to be my x squared. Outside is my sine function. Okay, we literally have those parentheses that we're smushing something into sine. So we're going to start by taking the derivative of sine. The derivative of sine is cosine. And I'm going to keep my inside function the same. That doesn't change. But now I need to multiply by the derivative of the inside. So the derivative of my inside function, the derivative of x squared, is 2x. So all I'm going to do, because for some reason it's so strongly ingrained in me that I have to do it, I'm going to put the 2x in front of my cosine. But I get 2x cosine x squared. And now you can see, if I were to take the second derivative, I have a product rule, because 2x is being multiplied by cosine of x squared. So I have a product rule, and so I have to be careful when I start to take these higher order derivatives that things can get a little bit more complicated. So just be prepared. Mentally prepare yourself for that possibility. All right, we're going to do one more. You're going to take the derivative of e to the 3x squared plus 4. And again, some of you might be a little bit faster at figuring out your inside and your outside functions. This time my inside function is that exponent, and my outside function is the exponential, e to the something power. So I'm going to start by taking the derivative of my outside. The derivative of the exponential is just the exponential, so it's still going to be e to some power. And again, we don't change the inside function when we take the derivative of the outside. So it's still going to be e to the 3x squared plus 4. But now I need to multiply by the derivative of the inside. So the derivative of 3x squared plus 4 is 6x to the first. So again, I'm just going to do a little rearranging. I get 6x e to the 3x squared plus 4 as my final derivative. And again, notice that if I were to take my second derivative, I would have a product rule in addition to the chain rule. All right, so the chain rule is one, it takes practice. You have to work through the problems. You have to keep practicing. So you have your homework as that worksheet. Use that. Come ask me if you have any questions, or ask Mr. Blake if you have any questions as you work through these. I highly recommend, before you even start, do what I did. Identify what your inside function is and what your outside function is. Use colors if you want, or just box or circle or something to keep you, focused on which piece is which.